quaternions were originally invented because they wanted a generalization of complex numbers that were capable of rotating vectors in the same way as multiplication with complex numbers can perform rotation in the complex plane. So what I now want to show is that the quaternion product indeed reduces to the multiplication of complex numbers if you have quaternions with only 2 elements. So let us start with the general form of the quaternion product. So it looks like this. You have a quaternion QA, and then I use this notation for quaternion product. So QA times QB. Then the quaternion product looks like this. So I take the so-called scalar parts of the 2 quaternions and multiply them together, usual scalar product. And then I subtract the inner product between the vector parts of those quaternions. Then I get the scalar part of the new quaternion, then I need to get the vector part of the new quaternion. Then I first have the vector parts times scalar parts from both. And then I'm going to add the cross product of the vector parts. So this is just how the quaternion product is defined. This is how mathematicians like to work. They come up with a fancy definition and then they show that if you define things like that, then things behave the way you would like them to behave. So let us then check that this actually works. So let us define some quaternions before we get 2 elements. Let us call them eta and r, subscript a and b. So those are the 2 quaternions that I'm going to multiply. So let us do that. So I'm going to get the scalar parts together. Minus inner product of vector parts, which boils down to just RA times RB, because the vectors are as good equivalent to scalars. Only 1 element each. And then I can immediately say that the cross product here of those 2 things are going to be 0 because they have the same direction. So then I'm left with those things. Now, I guess you can already see that this looks suspiciously similar to complex number multiplication, but let us just write it out anyway. So, on the other hand, for complex multiplication, I have then a complex number. I define the first complex number as eta a, a scalar part, plus I, imaginary unit, times RA. And for the other complex numbers, eta b will be its scalar part. And then it has the imaginary component RB. So I multiply those complex numbers together and then get the real parts. I'm going to get a real contribution from multiplying together the imaginary parts with a minus. Then we're going to have the cost terms, which becomes the new imaginary part. Times I. So then what you see here is, see what ends up in the first vector slot for the new quaternion, and what you see here is what you end up in the scalar slot of the quaternion. So this is quite nice. Quaternions work very similar to complex numbers, but you also see that when we work in 3 dimensions, then this cost product is making it a bit richer.